extraordinarily tired for some reason, but that's no excuse. If you don't get enough sleep, if you don't get enough to eat, it doesn't matter. There's no excuse. You have to do one Leetcode every day, right? Legend says if you go 4 days without doing a Leetcode, you could die. All right? You could seriously die. You know, you could have withdrawal symptoms from Leetcode that could kill you. So I'm just trying to ensure that doesn't happen to me. So even though I feel down and tired, we're going to get right into this problem. All right, so problem 1069. Relax. 1697. Checking existence of edge length limited paths. That's a mouthful. And there's a little bit of alliteration here. It kind of sounds like it's a rap song. Anyways, let's get right into it. So there's an undirected graph of n nodes, and it's defined by edge list, where edge list I equals ui, vi, and distance of I. Denotes an edge between node ui and vi with distance I. Note that there may be multiple edges between two nodes, okay? Given an array queries where queries j, blah, 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 you're tasked to determine for each queries j whether this is a path between PQ, if there is a path between PQ such that each edge in the path has a distance strictly less than limit. So for a system of edges, all the edges individually have to be less than some limit. Return a Boolean array answer, where answer length, queries length. All right, so just for each query, return true or false. Okay. So the funny thing is that this problem is very similar to another problem I did. And I can't remember. Is it the same problem? No, I've never done this. It's very similar to a problem I've done before, which is the beautiful thing about Leetcode. You just need to learn patterns. So I already know what I need to do here because I'm processing things in terms of not the total length of the path, but just the length of each edge in the path. So in order to process this graph, we're going to want to build it from nothing into the graph. If that doesn't make sense, it should as I kind of go through an example. So let's just look through this example. So let's just draw this out. So we have 1, 2, 0. All right, and then this has length 4, 8, 2, 16. So what I'm going to do instead of using this initial graph is take the edge list. So this graph as an edge list is ordered. I'm going to order it is what? Well, what's the smallest one? Well, there's a path from 0 to 1 with cost 2. So that's the smallest one. And then there's a path from 1 to 2 with cost 4. It's this one. And then there's a path from 0 to 2 with cost 8. And then there's this last path. Don't forget that one, 0, 1, 16. Okay, I'm not really concerned about this last one. But if I look at the queries and I sort those, well, it just so happens that the queries are 0, 1, 2. Right? I'm sorting it based on this length value, right? Not the nodes. And 0, 2, and 5. So since this is sorted, in order for two nodes to be able to communicate, to have a path between them, all edges in that path have to be less than a certain value. So when we build a query and we ask a question about a query, we should ask that question on a graph where no such edge is larger than that query's limit, right? So what I'm basically saying is like, let's create a graph up to this point, up to the point of the max edge being size 2. Okay, is it less than or equal to, or just less than? Strictly less than. Okay, so first thing we'll do is when we ask a query question, we'll say, we'll build the graph up into the point we have edges as the maximum number of edges such that all edges are less than 2, right? So we look at our edge list and we say, oh, let's look at this first value. Well, there is no such graph, so we don't have to worry about it. So what we can do is create this system of the nodes, and we add in edges as we process the query. So we look at this next thing and say, okay, now that this is 5, let's add edges such that the edges are less than 5. And since this system is sorted, right, since the edge list is sorted, it's a crazy delay, always with the delay. We can add the 0, 1, 2. All right. We can add the 1, 2, 4 because it's less than 5. And then we can't add 8 because 8 is greater than 5. So that system doesn't exist yet. And we're trying to ask in this query if 0 and 2 are connected. And as you can see, yep, right here, they're connected in this graph. So let's go through with another example. I'm going to disconnect this and reconnect it because it's very slow. And apparently my computer is very hot now. Is that faster? Nope, it's still ridiculously slow. Okay. So it's just going to be what it is. So this is a beefier example. So I'm going to leave the initial graph here and I'm going to do the same thing. So really this problem is we sort sorry, I'm all over the place today. When I ask the question if these nodes are connected, the easiest way to determine if these nodes are connected is to use union find data structure, right? Because when we have multiple edges, dude, the delay, I'm starting to worry that I'm not even gonna be able to post this because it's gonna croak on me. Switch ports, how about that? Probably map to that first port though. It's actually faster, believe it or not. Probably temporarily. Okay, so let's keep going. So first thing we're gonna do is we're gonna use a union find for the system and connect nodes in the union find as we add edges. Okay, so create union find for n vertices, however you spell that. So we'll create a union find for n vertices. We're going to sort edges, and sort queries, however you spell that. So we'll sort edges and sort queries. Then we'll look at each query, add edges with length less than query limit. It's called distance, right? With distance less than query limit. And then we check if 2 nodes in query are connected, if they're connected in the union find. So what we basically do is we have this system of nodes, right? Like this. And maybe there's a few connections between them. I don't know what the system looks like. I'm just drawing something random here. Okay. So everything in here, every edge here's weight is less than m. So all edge distance less than m. Okay. When I encounter a query that's larger, I'm going to add those additional edges into the system and then ask if they're connected. This is all over the place. This is not my best video, but the coding will be better, so hopefully. So let's look at this next example here. I already got distracted. Okay, so let's sort this edge list. So the smallest one is 1, 2, 5. And then 2, 3, 9. And then 0, 1, 10. And then 3, 4, 13. All right, and then the queries already in the right order. For some reason, I don't know if that's a constraint and I missed it. Well, they're not in the right order, so it's not a constraint and I didn't miss anything. Okay, so 0, 1, 4, 13, and 0, 4, 14. Okay, so we initially have these 5 edges, so we have. So this is what our graph's going to look like. It's really a union find data structure. 2, 1, 0. Okay, so we first look at this query and we say, okay, we'll connect everything up to 13. So then we look through this system, we say 1, 2, okay, that can connect because it's less than 13. Then we look at the next one, 2, 3, 9. Okay, so 2, 3 can connect. And then 0, 1, 10, yep, that can connect. And then we look at this last one, we say, okay, can those connect? No, because 13 and 13 doesn't work. So then since this is a union find, we can efficiently check in log in time. All right, are then 1 and 4 connected? No, they're not connected, right? So 1 and 4 are not connected, and that corresponds to this second question. So we're gonna have to do some reordering, right? Because this is the second query instead of the first query. And then we continue and say, okay, now we have 14, right? So now that we have 14, 3, 4, 13, 3 and 4 can connect, and then we ask the same question, are they connected? 0 and 4, true. Okay, so that's enough of that. Okay, so we're gonna have to use a union find. I'll try my best to make this fast. All right, so init self, and then n is the size. Now I'm going to use an approach I learned at Berkeley. So self.parent equals -1 times n. So each node, okay, starts at 0. Each node will have a -1 parent representing a weight of -1. All right, def root. So self of u. So the root of u, well, if self.parent of u is less than 0, then we return u because that means it's the root. Otherwise, we say the self.parent of u equals root of self.root of self.parent of u. And then we return self.parent of u. Okay. All right, is connected. If two things are connected, so if two nodes u and v are connected, that basically means we return that the self.root of u equals self.root of v. So they have the same root. And then the hardest problem is def connect self uv. So we want to connect two nodes u and v. Well, if they're connected, why do I keep doing that? They're already connected. We don't want to play this game. So I guess we'll do it now. That's fine. All right, if not, so if they're connected, we don't want to play this game of trying to think. So So the heavier root and the light root, we're going to sort self.root of u, root of v, and the key equals since it's negative, the smaller one will be more negative, which means it's heavier. So self.parent of node. So this will give you the heavier root and the lighter root of u and v. And then self.parent of the heavy root minus equals itself plus the weight of the lighter root, and then self.parent of the light root is now the heavy root. Do that on one line, but whatever. So this is basically just saying, okay, the heavy root is going to get the lighter root attached to it, so it needs to become heavier by however heavy the light root is, and now the light root points to the heavy root. Okay, so that's my union class. So we'll say u equals union n. Then we're going to sort the edge list. So edge list sort key equals lambda edge. And we're going to sort it by, just want to make sure, because there's this idea of returning things in the correct order. So we're going to have an answer. We're going to assume everything's false. Doesn't really matter. Okay, sort the edge, and we're going to sort it by the second or 0, 1, 2th value in the 0 first, second, or third value in the edge list, in the edge, because that's the distance. And then we're going to do the same thing with queries, but instead we're going to do the range of the length of the queries. So we're going to process the queries in order of the distance, but then also maintain information about their index, because we have to return things at the correct index. Key lambda query, same game here. Okay, well, it's the range. So index queries index at the second, again, the second location, because that will determine this information. Now I'm wondering if I should sort them in reverse order. Okay, so I'm thinking that I'm actually going to do this in reverse, because it's constant to pop an element from the back of a list, and it can be n runtime to pop something from the front. So I want to do this in reverse so that the last element in my list has the smallest value, and then I'll pop values from the list from the back to the front. Just going to make it a little bit easier. There's a bunch of ways to do this. So for index in queries index, so now this is processed in time. Our associated query will have the nodes u, v, and what do they call it here again? I already forgot. The limit equals queries at idx. Okay, so we get the query at that index, which is the smallest one. And we're going to say while edge list and edge list -1, -1. So the last element is less than limit So we're going to process through to get the things that are less than limit. We're just going to say, well, we'll connect. Oh, we have to pop it first. So the two edges are WX, the edges W and X it connects, and the distance equals edgelist.pop. So we're going to pop the last element. And then we're going to go to our thing, and we're going to say U connect W and X. And after we've processed everybody that can be in here, we're going to say, well, I processed all the edges that are less than your limit. So all the edges in the graph have a distance less than the limit. So the only way these things can communicate is if they're connected, because these are the only edges less than the limit in the graph. I'm basically being like, if you're saying like, I need to get from here to New York, and I can take toll roads, but I can't charge more than $15 on each of my card. This is a very particular example, right? For whatever reason, I can't charge more than a max limit of $15 on each transaction. Well, if I wanted to provide you with that path, I'd be like, look, I'll just start building paths where there's a cost less than $15, right? Because you can't exceed $15. So you can mark off all the paths that cost more than $15, right? All the toll roads, if you're not from America, a toll road is a bunch of bullshit. So, costs more than $15. A toll road is basically a paid road. I'm going to remove all those roads from the path because you can't take them. So whatever's left then are roads that you can take, and those roads must have a value of less than 15, right? So if I can connect you by only using all the roads that are less than $15, then you'll be able to get there. Okay, so if they are connected, or we'll just say queries at IDX, or no, what am I doing? Answer at IDX equals U is connected, U and V. And then at the end of that, we return A. And then we cry because it's broken. How did I know? It's like, I know I'm stupid. What's wrong with this? Lambda. It's a silent B. Lambda. Union is not defined, capital U. Union is not defined. It's not defined, man. Oh. I do that quite commonly for some reason. Someone should make a language where everything... Well, no, that would be bad. Boom, boom. Why is this longer? It's longer than it needs to be. Oh, because answer is the length of queries, not the N. Those aren't the same. Okay, this is where we pray. Let's go! Dude, I'm so smart and dumb at the same time. You ever do that? You like think you're a genius and then you do something stupid. You're like, I'm the dumbest person in the world. I can't decide. Just take the average of both and I'm just neutral, you know. Not smart, not dumb. Okay, so what's the runtime of this? Well, so this is going to be sorting. So n log n. So edge list, let's say n equals the length of edge list. Oh, I shouldn't use n because, you know what? I don't care anymore. M equals the length of the queries. So this is n log n time, right? This is m log m time. We're going to look at each m queries. And this is n edgeless. So mn times. So mn log n, final answer. Throw it in there. I'm done for today. I think I did pretty good considering I'm freaking super tired from a long week. But let's go. You're going to see this kind of problem other places, so memorize this pattern because it's a pretty cool one.